My name is Eric Anholt. I'm with Intel's Open Source Technology Center. I'm going to be talking today about building 2D rendering for the x.org X server using OpenGL. A subtitle of this might be throwing away 200,000 lines of device-specific code and replacing it with 5,000 lines of device-independent code. So X has always had 2D acceleration done in device-specific drivers, right? We have these acceleration architectures in the X server that tries to take the really complicated x.org rendering model and map it to a few primitives that your hardware can hopefully accelerate. The common primitives recently have been we do solid fills, we do copy area, and we do the render extension, which is a blending operation. Some things have tried to accelerate more than that. The old XAA that we threw away many years ago tried to do accelerated line support, so you could get zero-width lines drawn on your screen using hardware acceleration.
But that was really important. That was critical.
For your screensaver with the lines bouncing around the screen and them getting cleared behind. Yeah, line support was really important. And we threw away all that code at one point. So we.
Eric had wide line accelerated and polygons.
Oh god. Yeah, so there's a bunch of things that you could accelerate in X, and we decided at one point a few years ago that actually writing all this device-specific code for all these crazy operations that you really probably shouldn't be doing was insane and wasting our time. So we threw all that away. Recently, Chris Wilson's been working on SNA, Sandy Bridge New Acceleration, even though it covers not just Sandy Bridge, everything before and after. That is covering more operations than we used to, and it's been growing the size of our device driver. The problem here is that every single year we put out a new chip, and we have to rewrite that device driver, sometimes almost from scratch, to get basic 2D operations working. And then we had this GL thing, and for a long time it kind of sat on the side, like maybe if everything went right, you had a new enough kernel driver, and maybe your 2D driver successfully initialized GLX, and maybe if that worked, you could successfully get OpenGL working in direct rendering, and it was all this very optional thing. And that GL couldn't talk to any of the rest of the system. It had this private memory management where there was this block of space in your GPU that one client would come along, take the block, put stuff in it, do a bunch of rendering. Some other client would come along, clear the block, put its own stuff in it, and you'd lose all of your data. So it wasn't really a reusable acceleration system because your stuff would just get thrown away. When did we start GEM? Do you remember, Keith? 5 years ago?
7 years ago. 6 years ago.
6 years ago, yeah. Quite a while ago, we started building kernel memory management. It was initially the GEM was the name of the thing we built. And this moved all of that memory management into the kernel, and you had file descriptor-like handles to these blocks of memory that you could then hand off to the GPU to say, hey, go do some rendering in ID number 2. And you could even give a global name to those objects so that another process could open up that same block of memory and render to the same spot. This is what enabled DRI2. It's what was used for kernel mode settings so that your X server could allocate a block of memory and tell the GPU, hey, start scanning out pixels from here with this stride in this format. Along with all these new kernel interfaces, we got more userland usage of these interfaces. Primarily, the Wayland developers built a set of extensions to Mesa so that you could pass these buffers in and out of OpenGL. So what they wanted to do was be able to just have this little display server that talked to kernel mode setting, which is a more or less standard API. It's the same bioctals across all the devices. This little display server would handle all the mode setting stuff, and then all the rendering would be done with OpenGL. And all they would do is take these file descriptors out of their buffers that they rendered to, hand them to the display server, and say, hey, put me on the screen, please. So if we have these interfaces for doing rendering with OpenGL, and now OpenGL is everywhere, at this point there's open source drivers for the 3 major desktop GL vendors. Then on the embedded space, things are not so hot. We have 3D driver projects for all the vendors, but we don't have shipped 3D drivers for all the vendors. But things are looking pretty good. It looks like these days, when you look at the projects for new hardware, people are building an OpenGL driver first and an X driver second. So if we have this existing acceleration system for talking to your GPU, which is a lot of code, why not use these same Wayland-style APIs to take our buffers out of a generic rendering system and hand them off to our display server? So I started this little project 5 years ago now, which is kind of embarrassing. The idea was, let's take all these crazy X operations, the weird wide lines, the arcs, the core fonts that are not anti-aliased, all these operations. We could express them all in OpenGL shaders. If we could do that, then we could potentially stop writing 2D graphics drivers and just rely on this one shared code base that everybody's working on to get our rendering done. But working on actual hardware with mode setting is really irritating because you keep taking down your development environment. So I started building this using the Zephyr X server, which I think was an OpenHand project, where they built a little X server that sat on top of your X server. So you had a little window with another X session inside of your X session. Wonderful for doing development. I just fire up the X server, throw some applications at it, see if it renders right, close it down, start again. The problem was that 5 years ago, like a year after we had done the gem work, we didn't have those Wayland-style interfaces yet. I didn't have a way for the GL software to hand off a buffer from GL to somebody else. GL could talk to its own buffers, and there were Windows system-specific interfaces for actually presenting those buffers on the screen. For this, I wanted something that wasn't one of those existing Windows systems, and I got stuck and dropped the project. I was picked up by Zhigang Gong, a coworker at Intel, in 2011. By this time, the Wayland interfaces existed, so he pulled the code out of the weird branch that I had laying around, made a little standalone library for it, added support for DRI2, the current DRI at the time, using the Wayland interfaces of let's just take the GL buffer, get a name for it, hand it off to the X server, and the other way around. He also added large pixmap support. Your GPUs always have limits on how much they can render to. On this particular laptop, it's 8K by 8K pixels. X doesn't have those limits, and it turns out that people really do want to make pixmaps that are big. When you think about 40 megapixel camera images, Firefox doesn't want to have to chunk that up itself. Firefox wants to hand a pixmap to the X server and say, put this on the screen. So he added support for taking your rendering operations, splitting them up into little tiles, doing the operations incrementally, complete with all the what happens when my tile for my source is unaligned with the tile for my destination, all that stuff. A bunch of nasty code. I'm really glad it exists. And also wrote a bunch of performance fixes. When I had done the Zephyr work, I was trying to get something up on the screen. It was really inefficient code, and a lot of that got fixed. Since then, so that Zephyr work was done, I believe, for a closed source, the Glamour work in 2011 was done for a closed source driver. The Radeon developers actually picked this up and started using it. They didn't want to have to write 2D acceleration for their new chipset that completely rewrote the instruction set. So much easier to just take existing code, add a few fixes to it, and ship that. On Intel, we have a /configure option. The Intel implementation is kind of funny. It takes the existing 2D acceleration architecture, the one that's, it's called UXA. It's the one that does the copies and fills and render operations. It takes the existing memory management of that acceleration architecture, and just those 3 hooks, instead of being device-specific calls. It just calls into Glamour to say, hey, okay, my pixmap has this name here, and this pixmap has this name, and please go do a copy between them. On the Nouveau side, I didn't find any code for Glamour at all. But 2 out of 3 vendors have some support for it. When I came back to the project, there were a couple of things that really bothered me. The writing cross API GL code is hard. There were some attempts to port Glamour to OpenGL ES. GLES is the sort of crippled OpenGL subset. They just take the OpenGL spec, rip out a bunch of things they think people don't want, and say, here's a nice small OpenGL that's easy to implement. And it turns out that actually people wanted all those features, and then they slowly stuffed them back into the spec. The other thing was that testing X rendering code is hard, and I'll get into these 2 things. So OpenGL develops as a specification, as a library, by some vendors coming along and saying, I've got a great idea. We're going to make this new function that does, extends the blending so that you have 2 different source values or something. If one vendor does it, they put it under their own namespace, so GL, blend function Intel. If 2 vendors do it, they make it an ext function, GL blend function ext. If all the vendors get together and do it, then it becomes usually an arb function, GL blend function arb. Then later, if the OpenGL spec authors for the next version decide that it's a good idea, they roll it into the spec and drop that vendor extension from it. As an application developer, this sucks, because it turns out that what actually happens is that you get AMD writes the extension, NVIDIA writes a similar extension, eventually an ext forms from that, and eventually it gets rolled into core, and you now have 4 different names for your function. Oh, and by the way, the ways to get at all these functions depend on your Windows System API, whether you're using GLX or EGL or the Windows GL thing. So finding these functions is hard. So here's an actual example. GL bind frame buffer is something that every application you write is probably going to use. And it started as a couple of vendor extension. And then the ARB came along and said, this is really good, but we're just going to tweak a couple of things. And so as a result, we're going to write our own spec and rename all the functions to, in this case, they decided not to put ARB on it. Great. And that got rolled into GL 3.0. It got rolled into OpenGL ES 2.0. And then for OpenGL ES 1.0, which still exists, by the way, we need to support it for a bunch of Android systems, apparently. It's called GL bind frame buffer OES. This is really irritating to write support for. I don't want to, in my application, have to know about all the different variants of all these extensions that ever existed at my call sites, or even to have some sort of loader that I have to write that sets a function pointer. So there's a number of these libraries out there that set up a bunch of function pointers for you and load them with the functions on demand or at initialization time. They all have serious issues. So I decided to sit down and finally write a good one. It was, do I start from an existing implementation and replace every single line of their code, or just write it from scratch? I wrote it from scratch, and I feel a little bit guilty, but I'm still pretty happy. So it's a single library ABI that works across all the versions of OpenGL, all the versions of OpenGL ES, and it has support for all the different Windows system bits, specifically Windows GL, GLX, and EGL is the embedded GL that works on various different platforms with a bunch of nasty typecasting that's really broken. So Kronos started putting out these XML files describing their API, which is awesome. Now I can write a little generator script that knows all about the API and just generate this code for doing all the dynamic loading with all of that support for, oh, hey, if I'm on a GLES 1.0 version, then I need to look up the OES version of the entry point. But if I'm on GLES 2.0, then I can look up the undecorated entry point. Now, as an application author, I don't ever have to think about that again, except for at my initialization time, I do need to make sure that if I am on ES 1.0, that I do have the frame buffer objects extension. It's simple to drop in place. It's a matter of just changing your linker flag and the include file, and there's package config for that and everything. It's up on a GitHub repo. I'm hoping to put out a release soon after I resolve some bugs in those XML files that it turns out I'm using features that nobody else does. The other hard part of working on Glamour is that testing your X rendering is hard. If you ask any X developer, they'll tell you to run the X test suite. It's this old conformance suite from 1989. It's KNRC. It's really hard to read for those of us that were born later. And it's really hard to run. You have to set like minimum of 4 environment variables, but possibly 7, and I don't know if I've even found the right set yet. And there's a bunch of documentation, but a bunch of it is wrong. And there's a bunch of references to scripts for setting those environment variables for you, but all the scripts don't exist. And what actually happens is that X developers don't run their own test suite. They just spawn their X server, run a few terminals, run a window manager, drag some stuff around, and say, it looks pretty good. There had been some improvement to the test suite. Peter Hutter, Dan Nicholson, and Peter Harris, along with some others, including NVIDIA binary driver developers, had done a bunch of work on making the test suite buildable by mortals. It used to be an iMake, and they fixed that. You /autogen make, and you get a test suite out the other end. There's my testing environment. What you get when you actually run the test suite, though, is this. This is an error report, or a trim of an error report, about how some rendering went wrong in copy area, I think it was. When I first saw these, I thought, I wonder where the actual images are from the output of this test suite. And it turns out that these are the images. The way that the images are stored, this is just plain text files, error.log. And you have a width, height, and depth. And then you have run length encoded pixel values. So that 0 is a black. So that's my drawn image first. And then I have a reference image, also at 100 by 90 at 24 depth. And then I have run length encoded. I have a bunch of zeros and then 25 pixels of ones, which is not white. That's actually black with just a little bit of blue, invisible to the eye. Not what I was hoping for to do X testing. So another side project before I started working on Glamour, I took the X test suite, built it, and then I took the GL test suite, which has this nice testing framework. It's little Python scripts for collecting tests and setting up how to run them and setting environment variables and all that stuff. And from that, I was able to run the tests and collect these error logs and generate output. Keith came along, wrote a converter to take those weird error logs and generate actual PNGs with some arbitrary colors assigned to those pixel values so you can actually see the difference. And now, the output of your test suite, instead of a bunch of text logs and unparsable errors, is, oh look, I have my initial X test suite, I have Glamour, which introduced some failures. I need to look into those. And I have some change that I was working on that introduced one more failure in X copy area. I should go look at that. And then, in my HTML output, I now have my rendered image and, my reference image and my rendered image, and I can see that I failed to render that black rectangle. This seriously shortens the debug cycles.
It's useful that the error log information includes this way as math.
Yeah.
In 1989, that was not a bad improvement.
So I've now figured out how to do Glamour development. I can write OpenGL code successfully without having to worry about all these extensions. I can actually test the code that I build to see if it still renders correctly. And so I can start hacking on this OpenGL rendering core. But the interesting question I had for this was, can we go completely device independent for our X2D drivers? If I have a pretty much generic kernel interface, and I have OpenGL, which is ostensibly a device-independent rendering API. Can I make X run without any device-dependent code? Right now, each X2D driver has drmodedisplay.c, which is just this copy of this file that gets copied from one repository to another, and then people add a couple of little hacks to make things work, and then gets copied back maybe, or maybe copied to a third project. And so there's all these derivatives of this one file of several thousand lines of code. And it all should be doing the same thing. Similarly, I hope that every driver has a copy of Glamour initialization, which is pretty simple, actually. It's just take the file descriptor to the kernel and hand it off to Glamour, and Glamour goes and sets itself up. Each X2D driver should have a copy of DRI2 support, which is a bunch of glue about how to ask the kernel to tell us when a v-blank happens, and how to tell the kernel to please page flip at the next v-blank. A lot of really tricky code there that goes wrong very frequently. And every driver should have the same looking code in that, that file. Similarly, each 2D driver should have DRI3 support, which is a separate set of code. Similarly, present, also a separate set of code, even though they're all using the same kernel interfaces. Also, there's just nasty x86 initialization that nobody understands. You just copy it from one driver to another and say, oh, looks like it works.
Which has been the case since
Yeah, it's been the case since ever. So a while ago, Dave Early started this XF86 video mode setting driver, which once again copied an existing driver, and this time threw out all the device-specific code. It has a PCI-ID that the X server is saying, hey, could you probe a driver on this PCI-ID, and it goes and looks through all your DRM devices and says, there's one on that PCI-ID, opens it, sets up all the KMS stuff, it asks your hardware about all the video modes it does, and it didn't do any rendering acceleration because that would be device specific. So I started hacking on this project, and I took that FD to the kernel and passed it off to Glamour, turned off the shadow rendering code. And that actually pretty much just worked. I had more trouble getting all my symbols present than anything else. So that was pretty impressive. The DRI2 support was a lot more work. It turns out that actually the hardest part of DRI2 is that there's this, this nasty layering violation where the X2D driver sends a string over the wire saying what driver should be opened to Mesa's libgl, which then opens the Mesa driver of that name. I have a theory that maybe Mesa, that actually built those drivers, should know what name maps to what PCI ID and just be able to do that on its own. It turns out that we do this for DRI3, we do it for EGL, we don't do it for DRI2 with X. Let's just make that code generic and stop having this table of what 3D driver you should use in our 2D drivers.
It made sense before chaos.
Yeah, it made sense at one point. Many, many things did. And the other thing I added was present support. Present is the new DRI3 extension for putting pix maps on the screen that Keith will be talking about tomorrow. The driver implementation looks a lot like the DRI2 page flip implementation, except a lot more sane, not quite as sane as we think we can make it yet. Wrote all that. Everything but the page flipping is working on this laptop, which I'm not running at the moment because that would be crazy. So it turns out that I was able to get a mode setting driver doing most of the functionality of our current 2D driver without the same level of performance, no page flipping, and need some Glamour work. Oh, and no Xvideo. Haven't done that either. So the question at this point, now that I think I've shown that we could build a nearly device-independent 2D driver, except for that whole DRI2 driver name issue, can we make 2D Glamour perform like native? Like the custom code that we've been building for a long time. So we have this eye chart here from Chris Wilson, which you have no hope of reading. Let's see, green is the old UXA code. Our baseline is CPU rendering. So our 2D rendering is almost always slower than just telling the CPU to do the job for us, which is really unfortunate. The problem is that you have to eventually put things on the screen, and if you're mixing 3D rendering, then you definitely need to use the acceleration engine to put things on the screen, so eventually you have to take the hit of uploading it, and that's a lot of your cost. So it's not quite a fair comparison for our acceleration architectures, but it is pretty embarrassing that our hardware acceleration does make things slower. On the other hand, we have this Glamour code, which is mostly showing up a little bit faster than our green bars. So this is Glamour on Intel versus the old UXA code on Intel. Now, Chris has gone and done this SNA code, the purple, which you would hope that after all of this development is the fastest code you could get on our hardware. I think we can beat that, though. And here's why. So Glamour's faster than the UXA kind of, we'll just get a little bit of render acceleration working and call it done. It's not as fast as the year-round tuning that SNA gets. So I pulled up some rendering that I expected Glamour to be slow at, which was the core text glyphs. So not the kind of characters that you see on the screen here that are anti-aliased, but the old stuff that you see in ancient X applications like Xterm, for the most part. Oh no, Xterm is XFT now. Your motif stuff.
Motif apps.
Your old motif apps that still exist. So Glamour, when I picked the project back up again on my laptop, was doing 36,500 glyphs per second, which is about where we were with color rendering back in the 80s. And it's going through this horrible path. You take your character and your font, you upload it to a bitmap, then you read that bitmap back out, and you walk each of the pixels and find these run length encoded spans, and then you ask the hardware, hey, could you fill this span for each span? So obvious fix, hey, I'm going to walk the bitmap and collect all the spans and then ask the hardware to fill them all at once, and hey, it's 5 times faster. This is still kind of dumb because I'm making this temporary bitmap, uploading the image, and then reading it right back out and walking the spans. So here's a quick hack. Instead of computing these spans, I'll just look at each pixel, see if it's set or not, and tell the hardware, hey, fill this pixel, don't fill it, fill this pixel. That was faster. We could still remove the bitmap, and we can do even more stuff. Hello. There's a lot of performance projects left. You know, we were pretty close. We were doing better than our 1 year ago rendering architecture. But there's a lot of stuff we can do. I want to do direct texture mapping for software fallbacks. Part of the reason that I was looking at core text is that core text on this hardware right now is 8 million glyphs a second compared to the 300,000 that I got with a couple of quick hacks.
That's software.
Yeah, pure software. There's no acceleration here. It's just map the buffer, stuff bits in, and eventually they'll get copied out. So if I could do that in GL, then I would be able to drop all of this UXA code that I have for managing our direct mapping of textures and just ask the GL, hey, do you think you could possibly map this as an RGBA texture? And it would say, yeah, of course it's an RGBA texture, and let us do that. I think that would be a pretty easy extension to write. Some people have tried before and built some really awful interfaces for it. I'd like to really look into that.
I guess you're going to the dad's talk this afternoon.
Yeah. For that core text problem I was talking about, we could do even better than our software fallbacks, I hope, by noticing that these core text fonts don't ever change. They're like initialized at server startup and never change after that. So I could put them all in a texture and just, when I'm asked to render some glyphs, just tell the GPU, hey, put these glyphs on the screen, just quad, 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 without any of this temporary bitmap stuff that I'd been doing. There's a neat extension, arb-blend-func extended, for doing the anti-alias text that we use most of the time. That lets us take a 3-pass problem and turn it into a 1-pass rendering implementation. Our buffer storage would remove a bunch of our buffer mapping overhead that's taking 4% of my CPU right now, easy hack. Using vertex array object and vertex attribute binding that let us reduce a bunch of our calls into the GL. Each of your GL calls has a bunch of error validation, which is really nice as a developer that GL tells you, hey, you gave me the wrong argument here. When you're looking for performance, sometimes that's kind of irritating because
Just said nobody actually uses this.
uses which?
Oh, this is acceleration.
This is for
Yeah, all sorts of, so the buffer storage and vertex array object, every piece of rendering in Glamour would win from this. There's also weird repeat mode handling related to some user space buffer caching that they did in the Glamour stuff that I'm kind of dubious of. We could potentially notice when your buffers are the right size and just skip a bunch of this per pixel checking that they do. And a lot of the idea behind Glamour is that if we're only going to build extra rendering once, if we're going to just build this OpenGL code, we could potentially spend a little extra time and make all these crazy operations you shouldn't be doing fast if it means we're never going to have to write them again and never notice them. And we could potentially spend a lot more effort doing things that we wouldn't do otherwise. The trapezoid rendering in the render extension is really good at producing really pretty images and really hard to compute. Basically what we do right now is we have this software code that renders your trapezoid into a little temporary image. Then we upload that image to the GPU, and then we ask the GPU, hey, could you blend this trapezoid shape with this color into my destination? So you have these constant uploads going on when you're trying to do any of your SVG type vector rendering. And there's lots more FB code paths to write. The core text is just one thing. There's a bunch more fill styles, operations, and things that we could accelerate. So I'm pretty optimistic about performance. Taking sort of a worst case scenario of the core text that was completely unaccelerated before I walked up to it, I got a, what was that, 20x performance? No, just 10x performance improvement. And I'm still a factor of 20 away. I need to get, well, no, I need to get from 300K to 8 million. I think if we stop uploading bitmaps every single independent glyph, I think we can get there. It's the same sort of scale of improvement as the current 10x that I did, so fairly confident about that. And then there's a bunch of other Glamour projects too. We need to finish the page flipping support in the device independent driver. I have just a bug with the tiling of the frame buffer isn't allowed to change when you flip your pages, so I need to make sure that my starting screen is the same type of pixmap as my screen that I'm going to flip to eventually. That looks doable. Fixed the DRI3 API for Prime. A little mistake was made in doing the Prime support. The X server asks my Intel driver, hey, could you tell me what an FD is for talking to the Nouveau card? I have no idea. How about you ask the Nouveau card about that? Yeah. Need to add the overlay XV support. Right now, there's a bunch of effort going on for doing a device-independent overlay support for KMS. I believe the Sprite work is the name of that. And then there's a bunch of stuff about atomic/nuclear page flips, and I can't remember which one is which. We need to actually port to those APIs as the kernel implementations are landing. And then there were some more mistakes made, I think, in the Glamour code. The stuff that I'm relying on for my 2D driver for Intel is using EGL, and it's all using this x386 API, which means that I can't use that x386 API-based code in my Zephyr code because that's not an x386 DDX. I would really like for everything to be using the DIX APIs, so not x386, actually just generic X server code. And that's just a bunch of irritating typing. Finish the GLES 2.0 port. It would be pretty neat to see X rendering implementations that are ready to use on weird graphics drivers, possibly even closed ones, like you see on Android. And a fun hack would be, since I wrote a automatic compositing rendering implementation for Zephyr for presenting my rendered pix maps to the screen, we could take that, put that in the 2D driver, and just always have no tearing in your X environment even without a compositing manager, which some people still don't run. So the code, it's all in branches right now. I've got a pull request for the initial filter branch to get that external code back into the X server out to Keith, waiting on that. And then there's 60 patches to the X server and 5 patches to the mode setting driver and the new epoxy project that this all relies on. There's a lot of code out there. But I think it's a pretty fun project to work on. At this point, you can walk up to Glamour, find something inefficient, write a little bit of GL code. We're talking 50 lines to make some improvement on some X rendering path, and use the X test suite to make sure that you didn't break anything. And we have enough performance tools to test that you did actually make things faster. It's a pretty rewarding project to work on at this point. So if anybody's interested in getting their feet wet with becoming a crazy X hacker, I'd be interested in helping you. With that, I think I'm ready for questions.
So you said, you said that a bunch of your overhead cost is that the GL code does a lot of IO validation. Is that something that's plausibly if-definable out in a?
So what the GL developer, the spec designers are doing these days is making it so that you just don't have to call these functions as often. So, for example, the vertex attrib binding and the vertex array object one that I mentioned are extensions where you make this little object, and it's going to be the description of how to fetch vertices for this one rendering pipeline. And so you can say, oh yeah, you're going to get your vertex coordinates from here and your texture coordinates from here, and they're going to have a stride like this. And then when you want to go to rendering, you just bind that object as one call, and then you make one more call to say, yeah, and my vertex buffer is over here for this call, and then you can draw. As opposed to doing the, it would be like 10 calls to GL with a bunch more validation than either of those 3 calls normally. So that's been their approach to fixing it, and I think it works. It gives us the API quality still, while giving us the runtime performance of just not doing as much state changing per operation. Dave?
Does direct state access help?
Does direct state access help? So this is an interesting NVIDIA extension. Their idea was one of the extra calls you have to do when changing any GL state is that you typically have to first say which object you're talking about for the next calls, and then you make calls modifying that object. NVIDIA said, hey, that seems silly. Why don't we just have the first parameter of these calls be this object? Because it turns out that the calls had a parameter for which object anyway, because you had these binding points for your objects. So you had a vertex buffer binding point and an element buffer binding point and a copy read buffer binding point. And so you were already saying which binding point to look at that you'd previously bound. So why not just replace that with the name of the object? It's an interesting extension. It would trade off this GL call up here for increasing how many hash table lookups you do of the object name, which I think we could still do better on our hash table. I replaced it a while ago for a significant win, but I think you could even do better than I did. The other downside to this extension is that it's basically the extension for converting all the entry points that NVIDIA implements as of some GL version. So if we ever want to support some new extension before NVIDIA has ported direct state access to that extension, we will be exposing direct state access with fewer functions than NVIDIA will eventually support, and we'll end up with broken applications. I think it's a badly designed extension. There's also reasons, I think, to redesign it anyway. it would be really nice for a lot of for a lot of GL users like Cairo or GStreamer to be able to pass in which GL context your operation is on when you're making each call. So that way you don't have this global thread state of which context you're talking about, which, by the way, is a problem for Glamour too. Glamour and your indirect GL both fight about which GL context is the current one to talk about. If we could just pass the context in as the first argument, that would all go away. So the problem is that that's a huge pile of work. You have to redefine entry points for every single GL entry point there ever was. I don't really want to go there myself. Adam?
Have you looked at ext GPU shader 4, and do you know if your hardware is going to implement that in the future?
So GPU shader 4, let's see if I can get this right. That's the one that is,
You get real integers and you get bitwise operations.
yes, we already have that. So we have real integers from GLSL 1.30. GPU shader 4 also introduced geometry shaders and some other stuff. So we have all the components of GPU shader 4. We just didn't do GPU shader 4 itself because they made different decisions about how to do geometry shaders that were broken. So we've decided not to do that extension, but we do have the integer support. And that's the sort of thing that we would need if we're going to do trapezoids, where we need real integers and we need them real big.
The point where I was thinking of using it is actually in fixing the rest of FB. If we got Glamour to the point where you did not need FB underneath it, I think
That would be so cool.
I think what that lets you do is it lets you do the stipple and plain masks.
Yeah, so right now, the plain mask support that we have at the moment in Glamour is if you set the plain mask to anything but write all the bits, then we just bail and go back to the old software frame buffer code.
Which is things you never hit in real applications, but you can.
Right. But it would be nice to be just plain faster than image everywhere if it wasn't too hard. The plain mask stuff in particular I think is hard to do because you want to be able to read the destination and do operations on that, which your GPUs really don't want to let you do because they want to be able to queue up operations independently of each other with no ordering between them and then resolve the ordering at the end. If you need to be able to fetch your destination in order to do operations on it, then you would get a bunch more synchronization, and hardware might do that someday. It doesn't yet.
There's an Apple extension for Glass as well that it's like frame buffer fetch or something like that. And what it does is it lets you, in your pixel shader, you can grab the current frame, the target frame buffer value out.
Whoa.
Right? It's a cool trick. I think it only works on the Tegra.
Okay. I was going to say, nobody
but-
supports that, but apparently one person does.
You read that out, and then you still have the combiner state at the end, so you still have the XOR. It's just fetch. It doesn't replace that last
Yeah.
combiner state.
There's another interesting extension, the NV texture memory barrier or something.
Oh, yeah.
One of GL's rules is that if you bind your destination texture as a source texture to do things like we want to do, of read my destination, do some operation on it, and put it back. Normally GL says if you do that, you get undefined results. Like we have no idea what the caches are going to do to you. This NVIDIA extension lets you put calls in the application to say, okay, at this point, I want to guarantee that what I read from my destination texture is at least as new as the stuff that came before my fence. So you can potentially batch up some operations, do a fence, take your destination as a source, and do operations on those, including these kinds of crazy bit twiddling things, and then write one set of pixels into the destination and move on to refence again and do the next set of pixels. It's going to get tricky when you deal with sets of operations that overlap themselves, but it's possibly doable. I mean, it's definitely doable. It might be a lot of code.
I don't know. That's
Yeah.
stencil up with that and figure out how many times you overlap them.
Ooh. Oh, that's crazy.
Why not?
That's a fun sort of crazy. Yeah?
Sorry, just an end user. Like, why Intel support OpenGL
So basically, there's a lot fewer people working on Linux than Windows. We're catching up slowly. I feel like we've been making progress at a rate of like half a year of spec development per year. So 7 years ago when I started, we were like 10 years behind the state of the art on specs. We were in bad shape. At this point, let's see, GL 3.3, there's 4.0, 4.1, 4.2, and 4.3 and 4.4. We're like 5 specs behind, and they've been doing a spec every half a year, I think, more or less. So we're catching up at this point. And it helps that we have a lot more developers on Mesa now, and we're getting a lot more community contribution work from the AMD contributors and the Nouveau contributors on adding new extensions. Once somebody adds the core support to Mesa, that's most of the work, right? Writing tests, writing all that core software. At that point, a lot of these extensions are a matter of twiddling a bit in hardware. Once you have all this core support to know that your extension works and to add all the error checking and things. So now that we have a significant community around Mesa, I feel like we're catching up fairly rapidly. I'm feeling good about the state of things for Mesa.
Sorry, I have to stop you.
All right.
Thank you.
Thank you.